Good morning, everybody. My name is Ryan Skoug with ESI Engineering. I hope you've all been having a good year since the last time this group met last December. One heck of a year. But hopefully it's been a good one for you. Hopefully COVID and elections and lack of nice big vacations hasn't affected you too poorly. But hey, at least we're all together here today to be able to discuss some noise control and hopefully learn a little bit from each other. So today I'm going to be presenting some more on our review of low frequency impact noise. Last year, we looked at some of our findings that we had with some of the field tests that we've done. And so now we're going to continue our evaluation of the ASTM working group rating of the LIR, the low frequency impact rating, looking at how other researchers in this country and abroad have been looking at low frequency impact noise, and also how laboratory tested assemblies are turning out when we compare them to the LIR and some other impact ball rating methods. We've been looking at all of it. And so we just want to present some findings, show some of the areas we've been struggling with the LIR method, and also how other options for how we might be able to look at it. So we can start out looking at some rating methods. Just starting looking at what is the LIR? Uses a tap machine. It's what we're looking at for our ASTM working group. What it does is it looks at tapping machine noise from 50 to 80 hertz, does a 2 times multiplier on the sum, and then just 190 minus that summation gets us a rating, okay? The other 3 ratings that I want to look at use the impact ball as our source. And so we have this Japanese method. It looks at the fast max impact noise from an impact ball, and it's evaluated looking at 63 hertz to 500 hertz octave bands. And then that data is compared to an A-weighted curve. So it's not an A-weighted summation. It's kind of like the IIC rating where we have a curve fitting, and it's kind of a A-weighted curve that's curve fit to the data, okay? The other way to look at it is just doing a third octave band sum, which others have been doing and found good correlation with some subjective analysis. So you're summing the A-weighted 1/3 octave bands from 20 hertz out to 2500 hertz. So this is actually including some high frequency data. The other way to look at it that we've been doing is to just look at the low frequencies. So again, it's an A-weighted 1/3 sum, but just from 20 hertz to 80 hertz, just the low frequency data. Nothing, 100 hertz and higher that the normal IIC looks at. But then we're doing an inversion of this data just so that it's a rating, kind of like the LIR gives you a rating, whereas these 2 international sums, they give you a decibel number. So for these, higher is actually worse. Higher decibel means it's louder, whereas our rating methods, higher is better. It's a better assembly, providing better impact isolation. So just to look at what we'd done previously, last year we talked about Walker sound being audible down to at least 25 hertz. So below 50 hertz, we think at least 25 hertz we should be looking at, maybe even 20 hertz. The Walker sound at 25 hertz was within 7 dBA of the max. So this is audible sound that we're going to notice. The Walker sound was similar on the hard and carpet floors at low frequencies. They weren't drastically different by any means. They were very similar. And when we compare the ball drops to the tapping machine data, we found that the ball drop trended more like a Walker. The ball drop provided better signal to noise ratio at low frequencies, and the ball drop results are much more similar on hard and carpet floors than the tapping machine results were, which correlates well with the walking tests. So let's take a look at what some other researchers are saying. So if we look at this 1994 JASA report that was published by Warren Blazier and Russell Dupree, what they were doing was they were looking at low frequency impact noise inside of a condo. And what they were finding, you can kind of see this in some of their results here, is that although the construction of floated floors or the addition of carpeting is effective in attenuating mid and high frequency components, which we certainly see in our IIC ratings. Our IIC ratings are always better at mid and high frequencies from footfall noise when we had put a carpet on the floor. The data indicate that the amplitude of the floor response at the natural frequency of the structure is actually increased with the carpet. So any kind of rating method that we want to do, carpet should maybe even have a worse rating than the hard surface floor. So they went on, part of their report showed that, certainly IIC ratings are, near 80 when we do a carpet floor, but the occupants were just as strongly opposed to the floor as when it had an IIC 55 rating on the hard surface areas. This paradox exists because the low frequency impact noise levels typically were found to be on the same order of magnitude in either situation, whether it was hard surface or carpet floors. The low frequency noise was about just as loud. Another research report that we wanted to bring out in this presentation was written by some Swedish, Swiss, and German researchers. And they were looking at subjective and objective measures for evaluating low frequency impact noise in wooden buildings. So for starters, they pointed out that the most appropriate technical source to represent walking noise turned out to be the Japanese rubber ball. It was better than the tapping machine or the modified tapping machine that they were looking at. In its characteristics and spectrum, it is very similar to real walking noise. Additionally, there are no restrictions regarding floor covering materials, like carpet, unlike the other technical sources, like the other tapping machine sources. The best correlating single number rating for the Japanese ball is this AST max review or impact noise from 20 to 2500 hertz, which is the rating that I brought up earlier. So that's what we're going to look at when we look at some of this lab data coming up here. To continue, the regression line in figure 3 shows a slope close to 1, meaning when they were looking at the annoyance of their subjects in comparison to the noise level produced by the impact ball, it had a 1-to-1 slope. It was correlated. This tells us that an increase of annoyance of walking noise by 1 rating number leads to a similar annoyance increase for the rating rubber ball. Okay, they're well correlated, that's good. So this overall shift to higher annoyance ratings for the ball can be explained by the stronger excitation with higher loudness and annoyance of the rubber ball. For building measurements, this stronger excitation is advantageous as the signal to noise ratio is much greater for the ball than the other technical sources, which we've talked about as representative of what we were finding with our field test too. That signal to noise ratio was better with the ball, and that was helpful. This third researcher's presentation or report that we wanted to bring into this presentation is a doctoral dissertation done by Rikard Ökvist in Sweden. So what he was also doing is looking at objective and subjective measures of low frequency impact noise in a multifamily type building. So he says the standard tapping machine is the most common sound source for impact sound insulation measurements. Very true. It is well known that the tapping machine does not resemble actual walking sound, and its validity as a source can therefore be questioned. Should we be using it to look at low frequency impact noise if it doesn't even resemble walking noise? The rubber ball, so-called Japanese ball, was developed as an alternative that will produce a frequency spectrum more similar to human walking, especially below 100 hertz, which is the frequency range we care about. Okay, another primary point. Frequencies between 20 and 50 hertz are important for rated walking sound annoyance in lightweight constructions, which we found as well that we needed to look at these low frequencies below 50 hertz. For heavy constructions, it was indicated that the evaluation from 50 to 100 hertz 50 hertz rather than 100 hertz is appropriate for heavy construction. Current impact sound signal noise ratings from 50 and 100 hertz, examples being the IIC comparable in the ISO standards, or the IIC comparable with a correction that allows it to go down to 50 hertz. So even if it goes down to 50 hertz, these cannot represent annoyance in a way that is neutral to the construction system. Okay, that's something that we agree with. Well, just going down to 50 hertz doesn't just solve it when you're using a tapping machine. So, having looked at what some other researchers are saying, let's also look at some lab data. So thank you, Plytech, for allowing us to look at some of the data that you guys have done in the laboratory of some assemblies with some different flooring and ceiling options. So here we can see we've got a 6-inch concrete slab. And there's either no flooring, luxury vinyl tile and some thin rubber, or 1/2-inch thick carpet on 1/2-inch thick carpet pad. So we want to look at this in the 4 rating options, the LIR being using a tapping machine as a source, frequency range of only 50 to 80 hertz. The other 3 all with the impact ball. First one looking at doing a A-weighted curve fit for 63 hertz to 500 hertz data. Next one doing a 3rd octave band summation, that's A-weighted from 20 to 2500 hertz. And the last one just doing the same thing, but only 20 to 80 hertz. Okay? So our 6-inch concrete slab, get some numbers. what the numbers are, I'm not as worried about so much as just looking at how things change with the different flooring. So let's look at what happens when we put that LVT and thin rubber underlayment on there. Not much, which is what we would expect. We haven't drastically changed the assembly by putting a little bit of flooring and underlayment on there in a way that would affect low frequency impact noise, okay? Well, what happens then when we put the carpet and pad on there? All right, the LIR says now that we get somewhere almost around 20 points, 18, 19 points of improvement just by putting the carpet and pad on there. However, when we look at the impact ball results, the first one does get a little bit of reduction in the noise level, which when you look deeper into that, you see it's because of being out at 500 hertz. So that 500 hertz was changed between these assemblies, which changed the rating. Same thing with this one. When we look at this higher frequency data, it did reduce the noise. So the higher frequencies affected this. But when we just look at the low frequencies from 20 to 80 hertz, we don't see an improvement. It stays about the same. So impact ball low frequency data says we stay the same. Tab machine says we get a big improvement. That's not matching what the other researchers were finding or what we are finding in our field data. So let's look at a second assembly. So this assembly, we've got the same wood frame construction. The only changes are that we've got wood floor on a thin underlayment, and then we've got the same half-inch carpet bed. So when we look at our tab machine results, we look at our impact ball results, we get some numbers. When we put the carpet on the assembly, again, we get this 20-point delta, 21-point improvement in the rating when we use a tapping machine and look at 50 to 80 hertz. When we look at the impact ball noise, though, the noise level actually got higher. It got worse. This stayed the same. The rating change was 1 point worse. This seems to match what the other researchers were saying and what we were finding in our field data, whereas the tapping machine, this kind of result of a 21-point improvement isn't matching what subjectively we've seen in the field or what these other researchers are saying. Another assembly we can look at, identical wood frame assemblies. The only difference now, we've got gypsum concrete on 1-inch dimpled rubber, so a very soft underlayment. We've either got no flooring on it, or we've got our wood floor on thin underlayment. When we look at these results, we get some numbers. When we put the wood floor with underlayment on it, again, we're seeing a noticeable improvement, 13 points of improvement with the tapping machine method. We look at the impact ratings, though. It got louder, the rating got worse. So, these aren't big differences, but it's very similar either way, which is what we'd expect because we haven't changed the structure at all. We just put a little bit of flooring on there. But the tab machine result is showing a big improvement. That doesn't seem to correlate again with what our other researchers have been saying or our field data has been showing from our subjective responses. The last one I want to share with you, again, very similar structures, almost identical, not quite, but very close to being the same thing. The only difference is this one's got tile and rubber and gypsum concrete and the 1-inch dimpled rubber. This one is actually a roof ceiling assembly where it's got stone pavers on pedestals on the 1-inch dimpled rubber and then some roofing assembly on foam insulation. So very, very built up assembly and very soft on the top side. So when we look at this, again, we get some numbers, but when we put this roof assembly as a comparison, we see again a very big increase, 43 up to 80. Huge improvement in the tapping machine result. But if we do the ball drops on it, roofing assembly was louder. Same, not much difference. So if the impact ball is more like human walking noise and it is a better predictor of low frequency impact noise compared to subjects, this is showing something completely different than what the tapping machine is showing. So summary of our conclusions, what we're finding is our field test results and experience are similar with the findings of other researchers. The impact ball source is the most similar to human footfall noise. The carpet should not improve a single number rating, and audible sound below 50 hertz should be evaluated. These laboratory tests that we reviewed show agreement with our field findings that soft flooring significantly increases the low frequency tapping machine results, but minimally affects the low frequency impact ball results. So the conclusion, when we were reviewing this LIR method for our ASTM working group, The method only evaluates impact sound from 50 to 80 hertz and uses a tapping machine source. Because of that, the method does not seem to accurately evaluate footfall noise with various soft flooring options. So thank you for listening to this presentation, and if you have any questions that you'd like to talk about, I'd be happy to discuss it with you.